Hey everyone, another news update to report on this time. The RS-25 Retrofit 3B test series resumed for its final stretch, with a 550-second hot fire after swapping in a second new production restart nozzle. Exploration Ground Systems is wrapping up stacking preparations for the Artemis II solid rocket boosters and continuing to test mobile launcher upgrades at Launch Pad 39B. And a test article for the next version of SLS was seen in transport to Marshall Space Flight Center. Let's take a look at that. On Friday, February 23rd, NASA and Aerojet Rocketdyne, an L3Harris technology company, hot-fired engine 0525 again in the Fred Haise test stand at Stennis Space Center in Mississippi, picking up with the 7th test in the Retrofit 3B series. As you can see in the time tag on the test stand engineering camera feed, the test started at about 1:04 p.m. local time, Central Standard Time, and the engine ran for about 550 seconds from the start command to shutdown. The overall objective of these hot fire tests is to certify the RS-25 component production lines by testing hardware built by Aerojet Rocketdyne with updated manufacturing techniques. Although the live coverage focuses on the large cloud of exhaust products and 2 engineering camera views, left unsaid for pretty much every one of these tests is the test plan and objectives. Typically for these tests, the engine has a pre-programmed throttle profile with different power settings that are held for a set duration. During this test, for example, we saw a short throttle bucket where the engine throttled down from a high power setting to an intermediate one for a few seconds and then throttled back up. This could be demonstrating one of the flight throttle buckets that SLS flies. One example that is new to SLS is the so-called bolt bucket that occurs in the period around SRB separation. On Artemis I, as an example, the engine's throttled down to 85% at 123 seconds after liftoff as the thrust from the solid rocket boosters tailed off sharply. The engines then throttled back up to max power at 132 seconds right after separation. The positioning of a bolt bucket test on the ground is more a product of test objectives as opposed to flight objectives, and in Friday's test it occurred, as you can see in the duration timer in the upper right, from about plus 194 seconds to plus 203. Ground tests will also push engine components to the edges or corners of the flight envelope. Starting conditions for the engine are critical. The engine has a start box for both hydrogen and oxygen, which is a plot of the pressure and temperature ranges. For flight and flight engines, the goal is to start at a place in the box that provides the most margin. However, for development and certification testing, the development engines will sometimes be started on the edge of its pressure or temperature operating ranges, or in an upper or lower corner in order to demonstrate and verify that the manufactured hardware meets the required margins. Similarly with the engine run box after it has reached main stage. The engines have built-in redundancy, and those are demonstrated in some tests also, such as forcing the engine to operate with the controller's backup computer or demonstrating a safe shutdown using the backup pneumatic systems. The whole test series, in this case Retrofit 3B, has a set of objectives that also include run times for different components like the nozzle, so it will be operated at the restart engine's minimum and maximum power settings for a set duration. In some cases, the scope of test objectives is more broad than a test series, with the first new production nozzle, serial number 6001, being hot-fired across both certification test series. Retrofit 3B is the last hot-fire test series planned before assembling and acceptance testing new flight engines. It's also the second of 2 certification hot-fire test series. As a part of integrating the Space Shuttle main engine into the SLS program, NASA mostly retained the form, fit, and function of the SSME, now called the RS-25. That first adaptation phase replaced the engine's computer control system with new hardware and software, but otherwise is flying the 16 SSME Block 2 engines inherited from Shuttle as is. The SLS operating conditions are different than shuttle, so a test program was completed between 2015 and 2017 to certify the shuttle engines to SLS operations with the new engine controllers. In parallel with the adaptation of the existing flight hardware, NASA also contracted Aerojet Rocketdyne to restart production of the engines for expendable use on SLS. The 16 shuttle flight engines will be expended on Artemis I through Artemis IV, so new sets of 4 engines will be needed for Artemis V and beyond, and will also serve as the first set will also serve as backups for Artemis IV. Testing of production restart components began in December 2017 with the first retrofit series. The 2 shuttle ground test or development engines were progressively retrofitted with more and more engine components as Aerojet Rocketdyne stood up the different component production lines. The first series began with testing a 3D printed pogo accumulator integrated with SSME components. The next one tested the new accumulator and a new main combustion chamber. Those were called Retrofit 1A and 1B. The 4-test Retrofit 1A series ran from December 2017 through February 2018 using development engine 0528. Retrofit 1B was 9 tests conducted from August 2018 through February 2019 using the other shuttle asset development engine 0525. The A1 test stand was renamed the Fred Haise test stand in 2020 during a refurbishment and upgrade period, which also coincided with the onset of the COVID-19 pandemic, which changed a lot of schedules. Engine 0528 was used for the 9-test Retrofit 2 series that followed from January 2021 through September 2021. Engine 0525 returned for the Retrofit 3A series, with 5 hot fire tests conducted between December 2021 and March 2022. Aerojet Rocketdyne modernized manufacturing of the different engine components for the restart of RS-25 production, taking some techniques and lessons learned from production of other engines like the RS-68 and J2X development. About the only heritage shuttle elements left of Engine 0525 are the main power head pieces, the hot gas manifold, and the injectors, the main injector and the 2 preburners. The first all-new power head to come off the restarted production lines was at the center of a brand new development engine, serial 10001, and also called the certification engine by the program. Most of the engine components are manufactured at Aerojet Rocketdyne facilities in California and Florida and are shipped to the Stennis Space Center for final assembly and test. For the new engine's first test, a confidence test, a heritage nozzle was used. That test was conducted in December 2022. The first of the 2 certification test series then started in February 2023 with the first new nozzle, serial number 6001. After that nozzle was installed on engine 10001, that all brand new hardware was fired 12 times between February and June of 2023. For Retrofit 3A, engine 0525 was still using a heritage nozzle, but for Retrofit 3B, it was retrofitted with nozzle 6001 taken off the certification engine. That hardware mix was fired 6 times from October 2023 to January 2024 before a short break. The second new nozzle, serial number 6002, was finally delivered to Stennis and was installed on the engine for the second half of this Retrofit 3B series. The 2 long lead components for the new RS-25 engines are the power head and the nozzle. Nozzles are manufactured from a jacket that is integrated with over 1,000 cooling tubes that are brazed together. The jacket has been simplified from over 3 dozen parts down to 4, but the process of combining the jacket and aft manifold and the 1,080 cooling tubes is still long and laborious. This is a shot of a nozzle jacket. This is a shot of a couple of nozzles at Aerojet's DeSoto plant in the Los Angeles area. And this is a shot of nozzle 6001 either entering or exiting the brazing oven where the jacket and cooling tubes are integrated. A picture of nozzle 6002 was published shortly after the last test on January 27th, showing it already configured for installation. In between the last test and Friday's test, the first two production restart nozzles were swapped out while the rest of the engine remained installed in the test stand. This is a process that has been performed a few times recently as the two new production nozzles arrived at Stennis to be installed on the different development engines for certification testing. Pictures and B-roll video of the latest swap of nozzles 6001 and 6002 on engine 0525 were provided ahead of Friday's test. In this time-lapse B-roll, at the top we can see the engine vertical installer being positioned below nozzle 6001, while above it was being disconnected from the rest of the engine, primarily the main combustion chamber, but also the nozzle cooling supply and return flow branches. That service platform was then slid out so that a crane could be used to lower the nozzle down to the tarmac, where nozzle 6002 was staged for lift. Then the process was reversed. The crane was rigged to nozzle 6002, it was lifted up onto the vertical installer, the platform was repositioned under the engine, and the nozzle was moved into position for attachment to the rest of the engine. Thermal protection blankets are installed on the new nozzle's hat bands and drain lines, which is a more flight-like configuration. That was how 6001 was configured when it was first tested during the certification test series, but eventually those blankets were removed. They aren't necessarily needed for ground testing, and you can see that contrast between 6001 and 6002 in this still, with 6001 being lowered to the tarmac and 6002 waiting for lift. On Friday, NASA Kennedy Space Center Public Affairs also published another set of stills and B-roll video showing the two center solid rocket booster segments for Artemis II in the rotation, processing, and surge facility after the NASA worm logo painting was completed. These pictures were taken on February 16th. As noted in the previous video, the positioning of the logo on the middle segment of the SRBs has changed a little bit from Artemis I to Artemis II. The new placement on the Artemis II center segments allowed the painting of the logo to be finished now before booster stacking begins, which will reduce a little bit of closeout work necessary before the whole SLS vehicle rolls out to the pad sometime next year in 2025. Now that the painting is completed, those two center segments should soon be moved from the rotation building of the RPSF, where they are shown in these pictures, over to the Surge 2 building, where they will mostly sit and wait for their turns to be stacked for Artemis II. That will leave the two aft assemblies in the buildup stands in the rotation building and the other 8 motor segments in Surge 2. Preparation of the aft assemblies in the buildup stands was expected to be complete sometime around now in this end of February-March timeframe, and once it is complete, the aft assemblies will also dwell in the RPSF until a decision is made on when to begin stacking. Another video that NASA KSC Public Affairs published on Friday was a clip of a crew access arm swing test. In an emergency situation where the decision is made to evacuate Orion rather than fire the launch abort system, the crew access arm might not be positioned for the crew to get out of Orion into the white room that is situated on the end of the access arm. The test shown in this video shows the arm being extended at a rapid rate to get from a fully retracted to a fully extended position in a hurry. This is similar to the crew access arm for the space shuttle when they existed on pads 39A and 39B. In that case, the shuttle crew access swing arm could be extended in 15 seconds from its retracted position up against the fixed service structure. We saw this on numerous occasions when a shuttle countdown was ended after the beginning of terminal count, but before liftoff. This short clip shows one of those occasions during the first launch attempt for STS-88 in December of 1998. Yes, that long ago.
Bus taping is in progress.
And we have had to cut off the countdown. We did not pick up the countdown in time.
RSLS hold, BLS taping is in progress.
to meet our launch window.
Cut off. All stations proceed to the recycle control sequence, sequence 18.
Again, we have stopped the countdown clock at T-minus 19 seconds. We were not able to pick up the count in time to meet the very end of our launch window. The orbiter access arm is being replaced around the orbiter.
1, 2, and 3 assigned per sequence 3.
And safing operations are currently in work.
CLTOTC, perform APU shutdown.
For the crew access arm on the mobile launcher for the Orion SLS vehicle, the swing arm has to rotate through a larger arc than the shuttle crew access arm to be back in position after the countdown is cut off. And this test is one in a series to demonstrate the new capability that will be required going forward, since all the manifested SLS launches for now will carry a crewed Orion spacecraft. For Artemis I, Orion was uncrewed, and the crew access arm was not required to provide last-minute access to the spacecraft. For that launch, the arm was slowly and manually retracted out of the way before the launch countdown even started. Beginning with Artemis II, the crew access arm will remain extended to provide access to Orion throughout almost the entire countdown. After the crew gets on board their spacecraft, the swing arm will stay in place until the countdown reaches the T-minus 6 minute point, when it will be retracted out of the way. A Universal Stage Adapter article was also spotted on the Tennessee River last week, presumably headed to the Marshall Space Flight Center in Huntsville, Alabama. The USA will connect Orion to the new exploration upper stage of the SLS Block 1B vehicle. The USA can also encapsulate a 10 metric ton class secondary payload to fly along with Orion. NASA's Glenn Research Center manages the Universal Stage Adapter through the SLS program's Spacecraft Payload Integration and Evolution, or SPI, element. The USA is built by prime contractor Leidos Dynetics in Decatur, Alabama. In this graphic, we can see the USA part of the overall SLS Block 1B crew configuration. It is part of the Integrated Spacecraft and Payload Element, or ISPE, of the Block 1B and Block 2 crew configurations. For a story last year to get an update on the status of work in the SPI element, I spoke with Chris Calfee, the NASA SLS Deputy Manager for the office, and one of those odds and ends that didn't make it into the NASAspaceflight.com story was about work on the USA test articles being built to complete development of Block 1B ahead of its first flight on Artemis IV. Here's what he said last August.
Where they are right now is they've completed a demonstration test article. It's a full-scale Universal Stage Adapter, USA. They will actually ship that over here to Marshall Space Flight Center Test Lab, and we'll do some pre-qualification testing on that unit that I'll call. So it's pretty impressive. It's similar size to the LVSA, a little bit larger on the top end. It's an impressive structure. It's all composite with metallic flanges. That DTA looks just like a flight unit. Again, it's same size. So that's where we are there.
It's not confirmed that this was the DTA. After the demonstration test article was completed, Calfee said that Leidos Dynetics would be working on the qualification article, also known as the structural test article, which will be used for a full structural test series at Marshall. The flight article for Artemis IV would be the third unit, and that was likely to stay in Decatur until shipment to Kennedy Space Center a lot closer to the Artemis IV launch, which is currently planned for no earlier than September 2028. Block 1B secondary or co-manifested payloads would be encapsulated in the USA at a payload processing facility in the Kennedy Space Center or Cape Canaveral area before being taken to the vehicle assembly building to be stacked on top of EUS. Then Orion would be stacked on top of the USA. The first co-manifested payload is planned to fly on Block 1B's debut with Artemis IV, the IHAB Gateway Module. Following launch, insertion, and translunar injection on Artemis IV, Orion would separate from the rest of the vehicle, leaving the spacecraft adapter cone attached to the top of the USA. The concept of operations is that after Orion reaches a safe distance, the EUS would rotate the stack 180 degrees to point it away from Orion and jettison the top of the USA and spacecraft adapter cone. Then EUS would use its reaction control system thrusters to rotate the IHAB so it is again pointed towards Orion. Orion would then move in, dock to the IHAB, and extract it from EUS.